So this is the general layout of robotic-assisted approach to prostate brachytherapy. You can see that both the robot and the clinician are in the loop. And this is the way that it should be. So the robot is really an assistant to the clinician. It does not replace the clinician. So the design requirements in terms of the degrees of freedom that I mentioned are shown here in the graphical form. What we need are 5 degrees of freedom. These two, 1 and 2, are to orient the needle so that it can be, its position and the orientation can be specified at the point of entry in the perineum. 4 is to rotate the needles to achieve some kind of needle steering, as I mentioned. 3 is to insert the needle. And 5 here is to drop the seed. So where the seed is dropped is that the needle is placed at the end point of the needle is placed where the target is. The clinician then holds the style of the plunger and then pulls the cannula back to drop the seed. So the seed will be dropped at the point, at the tip of the needle, rather than being pushed further in. Okay, so that's the standard process. Now in the design that we use, we have the first 4 joints where we put redundant sensors and brakes to be able to create a fault-tolerant system. The actuators for the robot were stationary to reduce the inertia. Part of the reason for this was to allow us to attach a haptic device to it so that we minimize the external forces and get accurate haptic feedback. And we wanted to keep the mass of this system to less than 5 K because there was another robot that carried this for gross positioning. Now to orient the needle at the point of entry, we need to have what is called a remote center of motion. So this is the point where the needle actually is pivoted about that point. And that's, that requires some software, or you can do it through hardware. These are 4 possibilities in hardware, and we use this approach. And this is a CAD model of the system that we designed. All the parts that are shown here, these do not move. This double parallelogram here creates the remote center of motion so that the needle tip can be pivoted about the point of entry. And at the distal end, we have a motor that actually pushes the needle in, and another motor that actually drives it and pushes it and rotates it. This is the actual physical robot. So this was assembled and designed it and assembled in the lab. And on this side here, we have another robot that is used to provide gross positioning of this. So this robot carries this prostate robot and positions it near the patient. Now for the imaging side, we need a rectal probe, and this is the probe that we use. The probe is mounted on a motor, and the way that we generated 3D images was to get slices, 2D slices, and then compose them into a 3D image. So for this is a kind of an image of model of how this was done. The probe that we had was a probe that rotated rather than moved in and out. As in some cases you would get, in that case you would directly get rectangular slices. Here you get slices in a wedge, and then these are put together into a 3D image. So this is a little bit of time-consuming computation, but it can still be done in real time. So this is the total layout of the system. As you can see, it's a fairly complex system which involves imaging, control. It also involves a haptic device for insertion of the needle that the clinician can feel the force. This is an example. This is a video that shows the device and some of the properties of it. The device is balanced, gravity balanced, so that we can actually position it and move it in any way you want to. It's also fully back drivable, so we can pull the needle out in case the clinician wants to take over. So this is an illustration of the motion of the device for oblique needle insertion. So the needles don't have to go in parallel lines or in parallel trajectories. This is an illustration of the needle being inserted into a phantom. This phantom was built in-house with markers in there to drop, so you can drop seeds, and post-operatively we can determine where the seeds are dropped and measure the accuracy. There's also a graphical interface to this where using 3D slicer we can actually determine where the seeds are dropped and look at compare with the post-matrix plan. Okay, so what I want to do in the next few minutes is to talk about some of the work that has been done by a number of research groups in Europe and North America. This will give you an idea of how the kind of concepts that I talked about have been implemented by different groups in somewhat different ways. Most of the robotic systems that have been developed actually fall into two classes. One, where the needle is positioned, but the clinician does the manual insertion. And the others, where everything is automated. Clinicians tend to prefer the first. The accuracy is better than conventional. The maximum error that has been reported is about 2 to 3 millimeters, but most of the error is in the region of 1 to 2 millimeters. This is one of the first systems that was developed with Johns Hopkins. There is a company that actually was marketing this. I'm not sure if the company still is in business because there's a lot of competition since then. This system is fully automated. The needle driver actually inserts the needle. And the accuracy is about 1.2 millimeters. This is a robot that was designed by Brian Davis at Imperial College some time ago. I'm not sure that any clinical evaluation of this was done, but it's a robot that meets all the requirements in terms of oblique trajectories and motorized ultrasound probe, etc. This is probably one of the most sophisticated systems that has been developed. It was developed initially at the University of Rochester in collaboration with the group at Nanyang University in Singapore. As you can see, it's a robotic system that has quite a large number of degrees of freedom. So there's a cart that is 3 degrees of freedom, there's a platform that is 6 degrees of freedom, and then the part that inserts the needle has got 7 degrees of freedom. this is quite a lot it's a bit of an overkill. The advantage of this is that it has got very high accuracy of seed placement. It's probably the highest accuracy that has been reported. This is a system that's on the market. It was developed at Johns Hopkins in collaboration with a group in Austria. Once again, this needle insertion is accurate to about about 1 millimeter. The insertion is manual. This device actually orients the needle, and the insertion is manual. There has been some work done in MR-compatible systems. The advantage of this is that you can get higher accuracy, and you can also, if it's MR guided, you can also get much better control, much better visibility of the prostate. This has been tested at Brigham and Women's Hospital in Boston. They have an intraoperative MR suite where they can actually do this in real time. So they have intraoperative real-time MR imaging to guide the needle. There are very few ORs that are equipped in this way. The robot has pneumatic drives. Almost everything that would create a problem in the MR has been eliminated, and the system has been designed so that it only uses non-magnetic materials, and motors are pneumatic. Anything that is magnetic is kept outside of the MR suite. This is another MR-compatible robot by a different group at Johns Hopkins, and once again, the accuracy is very high, but the application is limited to ORs that are equipped like this. There's some work done at the University of British Columbia. I think Sarkunin and his group, they have developed a system where the insertion is manual, but the accuracy is not very high. But they have actually done a number of evaluations, and they've shown that this actually speeds up the procedure of brachytherapy very much. It's very easy to use. This is a company in Germany that has developed a robot which is based on an earlier design from the group in Austria. It's I haven't seen any clinical work reported for brachytherapy, because this was actually designed for treatment of pain, for percutaneous treatment of pain. But more recently, they have been talking about trying to use this for brachytherapy. And at my university, there is a group at the Robotics Research Institute that has developed a robot that is, in a sense, somewhat similar to the one that we have. The accuracy is fairly high, and this is the advantage they have is that they have tested this clinically and using 3D ultrasound imaging. This group is actually very strong in medical imaging, and they have developed a real-time imaging environment based on 3D ultrasound. And that's us. So, to conclude, one of the few things that's happening next is people are looking more at MR-compatible robots. Primarily because clinicians get a much better idea about the prostate. The needle insertion is much more accurate, but of course there are very few ORs that are equipped with this. Real-time imaging with ultrasound is possible with graphics processor units, and we have some ongoing work as well as people at UBC and in the group at Robotics-Assisted Institute, and there are a number of other people working with the group at Harvard looking at this as well. Now, I mentioned that in more advanced stages of cancer, it's possible to use brachytherapy with other methods. There has been work reported on extended beam radiation therapy, external beam radiation therapy with brachy, but there may be other approaches as well that one could use. We can expect more accurate needle insertion once some of these problems with tissue modeling, tissue deformation, etc. are addressed. So there is a lot of work now being done by, primarily by engineers, looking at how to insert flexible needles into deformable tissue, especially nonlinear, viscoelastic, non-homogeneous tissue. And this work, once this is done and implemented, we can expect much higher accuracy for needle insertion, in fact even through ultrasound. So I would expect a lot of work from engineers to go into this. This is an area that is particularly ripe for research for some of the graduate students that here might want to look at these issues from the point of view of control, modeling, etc. And these are some of the researchers who were involved in the work that we did. The work was funded by two federal funding agencies, the National Science and Research Council and the Canadian Institute of Health.